Now, am I audible? Okay. Uh, Now today we are going to see the mimic devices. In fifth chapter, already we have covered SOI technology, BiCMOS technology, then MESFET transistors. Now today we are going to see then strained silicon devices that we have seen. Now today we are going to see the mimic devices. Mimic means what? That we will see initially. One minute. आपको दिख रहा है स्लाइड्स? Now see, today we are going to see the mimic devices. Mimic devices means what? In the microwave communication system, whatever the chips are used, means in this all the devices, whatever the required devices are there, that may be the active or passive components. If that are fabricated on a single integrated circuit, that devices are considered as a mimic devices. Means monolithic microwave integrated circuits. That is nothing but mimic devices. Now, initially, microwave chips are nothing but the chips which are used for the microwave frequencies. Means that that will perform the operation which are required for the microwave communications. And for that which circuits are required, that if that circuits are fabricated on a single monolithic IC or in a single integrated circuit, then that is nothing but a monolithic microwave integrated circuit. Now, in that which components are fabricated? Components of different types, that may be the passive components like transistors, etc., and active components like uh, inductor, capacitor, resistor, etc., are fabricated on a single small chip to perform the complete microwave system or microwave subsystem operation. That is nothing but a MMIC chips. Then what is the advantage of it? Size is very much reduced, weight is very much reduced, and as these ICs can be produced at large or at mass production, therefore the cost is also reduced. So that is the advantage, main advantage. Now what is microwave integrated circuits? MICs are designed for operation at frequencies of approximately 1 gigahertz or more. Means for microwave frequencies, the microwave integrated circuits are designed. Now there are two types of microwave integrated circuits: hybrid microwave integrated circuits and monolithic microwave integrated circuits. What is hybrid and what is monolithic, that we will see. But in detail, we are going to see only the monolithic microwave integrated circuits. Now, the frequency range is near about 300 megahertz to 300 gigahertz. That is the means if that frequencies for that communication, whatever the circuits are required, that are fabricated by using the mimic technology. Now these devices can perform functions such as microwave mixing, power amplification, low noise amplification, and high frequency switching. That is the main advantage. Now inputs and outputs of mimic devices are frequently matched to a characteristic impedance of 50 ohm. Means what? In microwave communication systems, we require antennas, suppose transmitting antenna and receiving antenna, and we know that output of transmitter and receiver should be connected to the transmitting antenna, and there should be a proper impedance matching. Then that impedance matching is designed for the 50 ohm impedance matching. Means all these ICs or mimic ICs are designed for 50 ohm characteristic impedance or ohms. And if you want to cascade these ICs, means cascade means if you want to connect these ICs in series, more number of ICs in series, then that can be easily connected to each other, as it's characteristic impedance is of 50 ohm. And similarly, it can be connected to the input-output devices, which are required additionally at the time of transmission systems. Therefore, these ICs are matched for the 50 ohm characteristic impedance. Now, this makes them easier to use. Already I told you that cascading can be done. Additionally, most microwave test equipment means, again, for these ICs, the testing is essential. And the test equipments are also designed to have a 50 ohm characteristic impedance. These mimics are dimensionally very, very small, from around 1 millimeter square to 10 millimeter square. Means you can imagine the size or dimensions that are very, very small and that are mass produced. And in that small IC, large number of components are fabricated within the semiconductor or within the integrated circuit, and that can be produced in a large number of at a time, because all the fabrication processes can be done at a time. Therefore, these micro MMICs can be produced in the mass, and therefore the cost is very much reduced. Now, already I told you there are the microwave circuits, discrete circuits, hybrid MIC and MMIC. Now, discrete circuits means what? Suppose whatever the printed circuit board and above this whatever the components we are going to connect is, if you are doing a project, then in that project you are connecting, suppose, different components, transistors, field effect transistors, then the power amplifiers or power transistors, then again some passive components like capacitor, inductor, then resistor. If all are mounted by using a printed circuit board, then that is nothing but a discrete circuit. Means all are mounted. Then here, if any faulty device will be there, that can be easily removed or that can be easily replaced. That is the main advantage of discrete circuit. But area requirement will be very large. Again, component assembly will be there. If any disconnection will be there, again there will be problem, but that can be easily rectified and corrected also. But area requirement will be large. And again, as we know, for discrete circuits, large number of components if we are going to place on the printed circuit board, means PCB we have designed on this, the different components are placed for any circuit, then that for this the power requirement is also high. Now, for this, another technique is used in which hybrid MICs, hybrid microwave integrated circuits are there. In that hybrid, different ICs are designed for the diode transistors, resonators, capacitors, circulators, etc. Then microstrip circuits, etc. Different ICs are designed, and all these ICs are combined together by using a wire bond technique. Means all the devices are in the form of ICs only, but all these ICs are combined together by using a wire bond type of technique. Again, they are combined together on the some surface, like again PCB board. If you take a general purpose PCB, their tracking can be used, or you can design the PCB above this, all these ICs you can mount, and that circuit can be designed. So this is a hybrid in which no any single components are used or discrete components are used, resistor, capacitor, etc. All these are fabricated again on chip, but all that chips are separate chips are there. Then all these are combined together. That is nothing but the hybrid microwave circuits, integrated circuits. Now, last is the monolithic microwave integrated circuits. As the name indicates, all the devices, if any circuit you want to design, then for that circuits, whatever the components required, that components may be the diodes, transistors, resonators, capacitors, microstrip, inductors, then resistors, then again field effect transistors, different types of transistors may be there. Then all these components are fabricated on a single integrated circuit with very, very small size, and all these with internal connections. Whatever the circuits, up to now we have seen that internal connections are there, that interconnects we are making by using the metals or metallization, then that is done. Then all this circuit is fabricated on a single integrated circuit in which all the active and passive components are fabricated. Then such types of circuits are called as a monolithic microwave integrated circuit. Now in this topic we are going to see MMICs in detail. Now you can see here different components, how these components are fabricated, or if such shape is there, then what is the component. You can see the first component. This is a typical spiral inductor. This is nothing but a inductor. You can see this is nothing but a capacitor. If you can see this is a loop inductor, and this is a transmission, high impedance transmission line indicator. Means if such components are fabricated, all these components, you can see all these components are flat and they can be fabricated on a integrated circuit. There are different materials are used for different applications that we will go in further slides, that we will see in further slides. Then here these are the different components, for example. Then we will see MMIC in detail. Then substrate of an MMIC must be a semiconductor material. That semiconductor material may be a silicon, maybe a silicon germanium combination, maybe a gallium arsenide, maybe a quartz. These different types of substrate materials are available. Then depending upon the characteristics, depending upon our requirement, we have to select one of the semiconducting material as a substrate material. Then already I told you this MMIC can be made at low cost because the manual labor in the fabrication of hybrid MICs is eliminated. Means what? In hybrid MICs, individual ICs are fabricated. Means for this again labors are required. Means for this we require the fabrication techniques again, and all are combined together. Means for this again the manually someone should combine them together to form a complete circuit, or someone should assemble all together to form a complete circuit. For this again the labors are required. But if we use MMIC in which all the devices or all the components are fabricated on a single chip, then labor cost is very much reduced here. Size is reduced, labor cost is reduced, accuracy will be increased, and power requirement is also decreased. Power requirement is decreased because all the devices are very tiny, very small in the dimensions of micrometer, and therefore their power requirement is also reduced. This is the advantage of MMIC. Now in the diagram you can see this is one example of monolithic microwave integrated circuit IC, in which you can see that different components are fabricated above the chip. You can see this is a gallium arsenide substrate. This is gallium arsenide substrate. Above this you can see this is the resistor, this is air bridge, and this is microstrip input line, MIM capacitor. Then this is, you can see field effect transistor is fabricated. Means you can see in the single gallium arsenide substrate different components are fabricated above the substrate or on the single chip. Above the single chip all the different components are fabricated, and they can perform a single function, or they can be used to perform one circuit. Inductor you can use here via hole, ground plane metallization means base. For base again the metallization is then implanted resistor. You can see this is an implanted resistor, this is a thin film resistor. This is implanted means this is placed within the substrate by using ion implantation process. And here the thin film means this is placed above the surface, means here layer by layer structure can be created. So this is an example. Now another example, this is a photograph of monolithic integrated X-band power amplifier. This is a X-band power amplifier. Here you can see the different components are there. Here the coil will be there. Then again different components are here. So like this, the finally circuit will look like some. This is a X-band power amplifier. This is for power amplifier circuit. Then fabrication processes. Then fabrication processes directly, any circuit can't be fabricated. Initially that circuit should be designed. That circuit may be the analog circuit. Nowadays you can know that initially in earlier days the circuits are designed by using the bipolar junction transistors, but nowadays all the circuits are designed by using the field effect transistors, in which this is the directly analog circuit, and that analog circuit is directly fabricated by using the fabrication process. Because here you can see that you can fabricate the capacitor, inductor, resistor, different types of field effect transistors. Then in similar way other components also fabricated, and all these analog circuits means initially for microwave communication system, suppose any circuit you want, suppose for mixer circuit you want, power amplifier circuit you want, then for this initially the circuit is designed, the circuit is verified or tested, then that for that again layout design is done, then again that layout design is verified and tested by applying the different input combinations and observing the outputs. If output is as per our requirement, then that can be fabricated. So for fabrication process, here CAD tools are required, because here we have to design initially the circuit, then by having the different components we have to draw the layout, then that layout, so again for that layout we have to find out the width, length, thickness of all the components. Then all the components are designed by using the CAD tool, and once the design is completed, then we have to apply the inputs and outputs we have to observe. And again you can see that in the, if you want to fabricate such device, means here you can see, if you want to fabricate such device, different means this is a layer by layer structure, and every layer we require a photolithography. Means what? See, in this area only you want to insert a circuit for microstrip input line. Here you want to insert a capacitor, here you want to insert an inductor, the remaining area no insertion will be there, then that area should be protected. Where you want a particular implantation, only that area should be open, and there that by using that particular material you have to implant it. For resistive type of material we have to use, for capacitive, the capacitive material you have to use like this. Means for field effect transistor, gate material is different, again oxidation will be there, suppose it is a MOS, then source and drain will be there. Then here again we have to add the impurities, here the implanted resistor is there. Means for this we have to create a layer by layer structure. Then if you are on to create one layer, then other area should be protected, and within that area only you have to implant it. Once that implantation is done, if you want to create a capacitor, then a remaining area should be protected by using a mask, and only that area will be open, here you can implant it. In several times you have to use the photolithography process, and for using several times photolithography process, several masks are required. Several masks are required, because here if you want to fabricate this part, inductor part, then remaining area should be protected, then only this part should be open, means mask should be such that only it is having a shape like this, remaining area should be protected. So means different masks are required. Then all that mask designs are again done by using a CAD tool. There are different softwares available. Then this CAD tool includes circuit design and again optimization. Circuit design and optimization is what? By having a less frequency, that circuit should be connected to each other. Means circuit should become small, very less number of components are required, less interconnectivity should be there, or interconnection should be there. That is nothing but the circuit design, optimization, and mask. Every time, every layer we require different mask. All these three things, circuit design, optimization, and mask generation, is done with the help of CAD type of tool, which is a software tool. Then formation of active layer on a substrate by using either ion implantation or epitaxial technique. Already I told you, active layer means initially the substrate will be there, above this substrate one epitaxial layer will be there. That epitaxial layer will be formed either by using the ion implantation or by using a epitaxial growth. Then within that epitaxial layer the further circuit is fabricated. That already we know what are the advantages of epitaxial layer. Here the junction capacitance is reduced, latch-up problem is reduced, then we can easily downscale the component. Then all these advantages are there. Therefore, within the epitaxial layer, or this is called as active layer, then above the substrate some active layer should be formed, and within that active layer all the devices should be fabricated. And again, for isolation, that isolation can be done by using the etching. Means if one part is not connected to another part, then in between this directly the etching will be done, so that these two will be isolated from each other. So here how the MMIC design is done. Here the block diagram is there. Is customer or market requirement. Depending upon the customer requirement, initially on paper circuit designing is done. Then that, or depending on the requirement, some programs are written. That program will give you the circuit design. Then that circuit design you have to verify. Means for that circuit design, again the layout is drawn. That layout you have to verify, and again that layout should be given to the foundry. Then initially only one IC is prepared, that will be tested. If it is working properly, then it will go for the mass production and further assembly and package, because all these devices again should be packaged. If there is a faulty components, then that are rejected. Like this, means like this the MMIC product development process is there. Now you know all these processes. Means here several times we have to use the lithographic process, because one area should be kept open and another area should be masked, so that no operation should be done on this. And normally such type of lithographic process is done by using the projection lithography. Why the projection lithography? Because here the masks are placed above, and accuracy we want more, therefore light source is used, and here the masks are placed above, because the designing of mask is again a tedious task. Therefore whatever the masks are generated or fabricated, that masks are protected. So generally here the projection type of photolithography technique is used. Then ion implantation is required, because selectively so many times we have to implant the particular material in the particular region, and other area should be protected. So other area will be protected by using the photoresist mask, and where the windows are open, through that windows only the particular implantation is done by using the ion implantation process. Then molecular beam epitaxy, that epitaxy method is required to grow an active layer above the substrate, because substrate is a plane. Within the substrate that devices are not fabricated. Above the substrate some epitaxial layer is grown, which is active layer, and within that active layer the further devices are fabricated. Therefore here molecular beam epitaxy is used. Then ion etching method, ion etching method is used, and again suppose you want to remove all the part, then at that time wet etching is also used. Then ion etch is nothing but the dry etch. Suppose you want to isolate the parts, here you can see the first device, second device, third device, fourth or fifth, or components, different components are there, and all these components are isolated by using the etching. Then at that time ion etching is used. Then wet etching, sometimes some part you want to etch at a time, then within the wet etchant solution that wafer is placed and entire part is removed by using the wet etching process. Then like these processes are done. So here some comparison is there for monolithic and hybrid. You have to see only the monolithic parts here. Now you have to see the advantages and disadvantages of MMIC. Minimal mismatches and minimal signal delay. Minimal mismatches because all the devices are fabricated, and therefore they are fabricated with very accurate dimensions and accurate quantity of the material, and therefore there is a very less minimal mismatches of the devices. Therefore circuit will work properly, and our circuit is very compact. All the devices are very small, and already I told you the device dimensions are, means that circuit dimensions, integrate chip dimensions are very small, and therefore there is a interconnections delay is less, because they are all the components are very close to each other, and therefore very short paths for interconnects, and as the short paths are there, interconnect delays are again reduced, therefore very less signal delays or signal delays are reduced. There are no wire bond reliability problem, means as in hybrid MIC technology we have seen that different uh, devices are fabricated, or different components are fabricated on different ICs, and all that ICs are combined together by using a wire bond. But here all entire circuit is fabricated on a single chip, therefore no any interconnect bond is required. Therefore if there is a no proper connection or connection breaks will be there, then such problem is, or no contact will be there, such problems are not there. So that problems are reduced. Up to thousands of devices can be fabricated, means that if once you have designed a circuit, once you have verified that circuit by drawing the layout by using a CAD tool, then that circuit is finalized. And if that for that circuit you want 1,000 of components, you want 10,000 of components, then by using same fabrication techniques, once all the techniques, all the circuits are verified, then you can implement same technique for large number of ICs also, means you can use it for the mass production. And therefore such same devices, it is possible to fabricate same type of devices in the thousands of numbers. And as it is produced in the mass production, then naturally the cost per device will be reduced. So that is the advantages. Then another disadvantages is what? Optimal material cannot be used for each circuit element. Means suppose you want to fabricate a capacitor, you want to fabricate an inductor, then suppose for this you require a mass, some opening areas, and suppose for both if you want to use the same material, you can use the same material because the fabrication technique will be there. But suppose you want to use capacitor, which is the most suitable material, and for inductor, which is the most suitable material, then you have to use it separately. Use it separately means what? For initially you have to fabricate the capacitor or inductor, and afterward you have to fabricate the capacitor or inductor, whichever left. Means separately you have to fabricate. But here, as you are doing the mass production, sometimes if one can use the same material for most of the components, then so that the process becomes easy, then same material is used. Means optimal material cannot be used in that case. Suppose simultaneously you want to fabricate inductor, capacitor, etc., or suppose any another devices, and for particular devices particular material is used good, but as you want to fabricate all the devices simultaneously, you have to use a same material for all the devices or all the components. Therefore you can't use the optimal material here, because you are fabricating all the components simultaneously. So that is the main disadvantage. Power capability is lower because good heat transfer materials cannot be used. Power capability of the materials is lower. Trimming adjustments are difficult, means you cannot downscale so much components. Unfavorable device to chip area ratio means that semiconductors or substrates are available in the standard size, and above that, suppose you are fabricating, then unfavorable device to chip area means sometimes the substrate area requirement, substrate area will be more, and above that large area you are going to fabricate very small device. So that is the disadvantage. And tooling is prohibitively expensive for small quantities of MMIC, because if same number of components you want to produce 100 components, then at that time all these processes you have to do. But that type of components, if you want to produce 100 only, then naturally the cost will be increased, means at that time it will be expensive. Now here materials used for MIC, different materials are used for the different layers. This for substrate material, here you can see the list of the materials: sapphire, alumina, silicon, quartz, GS, etc. can be the substrate material. Then again telluride, all these are the some substrate materials. Then conductor materials, Here nothing but the metallization, which are good conductors, that are nothing but the metals: copper, gold, silver, aluminium, sometimes platinum also used, sometimes alloys of both are used. So like this is the conducting material. Dielectric film, for what purpose we want to use the dielectric films? For isolation purpose, for within the components, or from device to device, or for protection to device, also for protection of active devices. Again the dielectric films are required. And for fabrication of capacitors, again the dielectric films are required. If you want to fabricate the MOS, then again metal oxide, means for this again we require the silicon dioxide. Means dielectric films are fabricated by using the silicon dioxide or silicon oxide. And resistive films, if you want to fabricate a resistance, then resistive films are nichrome or tantalum. These are the some of the materials used. Then commonly used substrate materials are different organic PCBs, printed circuit boards. This is FR4, RT Duroid. Each material is having its advantage and its disadvantage. Then another material can be used, a plastic substrate also can be used. Then alumina is the next material. Again, for different frequency applications, different materials are used. Each material is having its own advantage and its disadvantage. Then fourth material is quartz. Then fifth material is sapphire. The most expensive material is the sapphire. That is the main drawback of this, but again it is having some advantages. Then beryllia and aluminum nitride is again another substrate materials, and GaAs. But most of the time GaAs is used as the substrate material. Our most favorite material in this MMIC technology is the GaAs, because already we have seen MESFET. What are the advantages of MESFET, etc., that we have seen. And again GaAs is having very high electron mobility, therefore signal transmission is very fast. Here in this, or switching speed is very fast, means it can increase the overall speed. Therefore GaAs technology is mostly, or GaAs as a substrate material is mostly used. Here you can see why GaAs. GaAs has become the material of choice because of its ability to perform at high frequencies. For high frequencies it will give a good response. Its electron mobility is higher. Then size and weight reduction, its size is also small, weight is also less. Cost reduction, already some more technologies are designed for the GaAs. Therefore already some well proven technologies are there, and that technologies directly can be used for the MMIC also. Then wider frequency bandwidth performance, high resistivity, semi-insulating property that reduces crosstalk between the devices. All that are the advantages of GaAs, and therefore most of the time the most favorable material for substrate is the GaAs material, gallium arsenide material. Here the comparative chart is given. Types of materials: alumina, sapphire, glass, beryllia, GaAs, Si, and quartz. And for which type of applications. Suppose you want to design the microstrip lines, if MMIC's complete entire circuit you want to design, then microstrip circuits you want to design, then at that time mostly suitable materials are GaAs and Si or MMIC, in which all the devices are fabricated on single chip. Then again, in different applications of microwaves, then different substrate materials can be used. But GaAs and sapphire is the costlier one. Therefore, where we can use the another materials, there you have to use the another. Where these materials are required or advantages of these materials are required, at that time the GaAs or sapphire is used. But again, the GaAs is the most favorite or mostly used material. Now conductor material. Conductor material, we have seen that conduction means for interconnection, this conductor material is used for interconnection between component, from one component to another component. Already you have seen in the if we see the inverter, CMOS inverter, then for CMOS inverter, for connecting VSS contact, VDD contact for input output. You can use the metals. That is nothing but the metallization, which are nothing but the interconnects. And here again, for making interconnects, some conductive materials are required. Then this conductive material should possess the following properties. It should have a high conductivity, high coefficient of thermal expansion. High coefficient of thermal expansion is what? For small values of temperature, it should not melt. It should have a melting point higher. Low resistance at RF microwaves. It should provide a low resistance at RF microwave so that the conductivity will be good. Good adhesion to the substrate, because all the device is fabricated above the substrate. Then from substrate, above the substrate only these lines are passing. Then it should get properly attached to the substrate. Good etch ability and solder ability. Again, suppose you want to take at output, input output connections from these conducting materials, then for this again it should have a good solder ability also, easy to deposit or electroplate. And these are some of the examples. Here again hybrid MIC are shown, MMICs are shown. CR is somewhat cooled steel. CR is cooled steel sheet. Here AU is gold. Then here the combination of these can be used as a conducting material, or separately again these materials can be used as a conductor material. Again here the properties of conductor materials are shown or given. This chart is for your reference. Then dielectric films. Already I told you where the dielectric films are required: for fabrication of capacitor, for protecting layers of active devices, and for insulating layers of passive circuits. These dielectric materials are required, and this should have a reproducibility, high breakdown voltage, low loss tangent, ability to process without developing pinholes. All these are the requirements of dielectric films. Then these are some of the dielectric films, but among these dielectric films, the mostly used dielectric films is silicon oxide and silicon dioxide. Sometimes silicon nitride is also used. Last two are not that much used. Then resistive films. Resistive films means if you want to fabricate the resistor, then resistive films should be fabricated there. Thin film resistors. Then it should have good stability, low temperature coefficient of resistance. Sheet resistivity should be high. And where these resistive films are used? For terminators, attenuators, and for bias networks, we require resistive films. And these are the materials. Already I told you what is CR. CR is cooled steel sheet. That steel sheet is fabricated by using some different technology. So that is CR. Then again, here are the different properties of here are the properties of resistive films, different resistive films, CR, NICR. Then depending upon the requirement, that particular resistive film is selected. Then properties of various manufacturing technology. Here already I told you thin film hybrid MIC, thick film hybrid MIC. These two are hybrid. Hybrid means individually diode transistors, capacitors, inductors, all are fabricated in a different chips or different integrated circuits, and then all are assembled together to have a complete circuit. This is nothing but a hybrid MIC. And monolithic microwave IC, in which all the devices are fabricated on a single integrated chip. Means if you see a chip of 1 centimeter by 1 centimeter size, or 2 centimeter by 2 centimeter size, in this all the circuits are fabricated within the chip, and this chip is having a characteristics impedance of 50 ohm, so that it can be cascaded to another IC, and again it can be connected to the receiving and transmitting antennas also. So you can see these are the capabilities, or these on different parameters these are compared. You can see here this is the mostly used or mostly suitable. 1 minute. Hello, am I audible?
Yes, ma'am.
Uh-huh. Here application of MMIC, already I told you, in the microwave frequencies, all these monolithic integrated circuits are designed. Then optical and broadband communications can be used in the low noise amplifiers, low cost packaging for transmitting and receiving new 20 to 30 gigahertz system. Means in communication system, if all the device, all the there are different blocks for transmitting transmitter, different blocks for receiver. All the blocks can be fabricated on a single chip. All the blocks can be fabricated on a single chip in case of transmitter and in case of receiver, and such devices are used in our cell phones or in mobile phones where we require to transmit and receive, and all these ICs should be very very small. Means that ICs are used, mimic ICs are mostly used in the cell phones. So here these are the applications. So here we have completed the mimic devices. Now in next lecture we will see the MOSFET, modulation doped field effect transistors. Then our fifth chapter is completed. Now here on Monday again I am having some work from college. So I'm going to engage your lecture at 10 o'clock. It is exchanged with Chaudhary sir. I think at 10 o'clock you are having the lecture of ISD. Then my lecture is from 2 to 3. 2 to 3 will be engaged by Chaudhary sir, and I am going to engage the 10 to 11. Then it is not possible to conduct the practical on that day, but actually I want to show you the virtual lab and your presentations will be there. Then that I will conduct on Tuesday from 10 to 11. Okay, that practical I will shift it on 10 to 11, and my lecture is again Monday on. I will inform accordingly. I will conduct the lecture from 10 to 11, because again from online exam of MEMS I'm going to the college on that day, and paper verification will be there. Therefore from 2 to 4 I am engaged. Okay. So we remember that. I will inform in group also. 1 minute, let me take the attendance. Okay. You can leave.